Okay, welcome to class meeting 19 of EECE574. We will have quiz 2 next Tuesday at this time. Handouts, lecture videos are available, and homeworks will be assigned today. There was no corrections I have found except some typos, so I have revised the section 6.3 and 6.4 frantically before I come to the class, but there are still some inconsistent definitions and notations. So I will be uploading the PDF after this class, so you cannot download it right now. Anyway, our topic was moved to the correlation functions and the measurement of correlation function. These two topics were supposed to be finished in a class meeting, but it seemed I talked too much last time. Anyway, let me be finishing these two topics today. Let's review what is studied. So we defined the autocorrelation function of a random process. So here I say that most of the times throughout this section, the random processes are real valued. However, for you to be better acquainted with the definitions for complex valued, I will be putting conjugations here, but you may not need that much. Got it? So this is the definition of a general continuous time random process that is complex valued. So when you are given x of t, usually you put conjugation on the right factor. Got it? So you have two factors, you put conjugation on the right factor. And whenever you replace one of the parameter with some delay parameter tau, what you do is that you define t1 as t plus tau and t2 as t. So you have r sub xx t plus tau comma t. So inside expectation, you have two factors. The first one has argument t plus tau, and second term has conjugation here. By the way, I have been kind of using some strange notation for a long time and was criticized once. And let me be just quick. For example, suppose you name a function f that is, for example, complex into complex. Okay, for example, you have f of z equals cosine z, something like that. Got it? And what if you want to conjugate it? What is your notation? Is your notation something like that, or is your notation something like that? So which one? I prefer the first one for some reason, but it seems this is not good, because you may say something like this, and you define f conjugate as this one. Okay, so f is the function's name, so f conjugate of z is much better notation than f of z conjugate. But sometimes I will still using this notation too. So whenever you see that, I meant the second one. Got it? Anyway, this was the definition of the general complex valued autocorrelation function. And here goes another definition. This is the here goes the definition of a finite power random process. So you compute an instantaneous power that is modulus squared of x of t, and you take the ensemble average. And if this as a function of t is always finite, then you say that the process is a finite power process. This definition I didn't mention last time is a continuous time general complex valued random process is called white. And this white is somewhat strange, because usually when we talk about a white noise or white spectrum, we talk in frequency domain. But here, the white means that if you compute the autocorrelation function of a random process X, then even with a very small difference in time, the correlation is 0. Okay. Whatever T1, T2 you have a delta of T1 minus T2 times something. By the way, when I saw this definition, actually this is from Populis, our textbook, I first thought this Q of T1 is strange. And that question lasted for around 30 years because I took the graduate level probability course in 1995 in the fall semester. So it's almost 30 years now. And that was strange. I thought, okay, probably the autocorrelation function in general, even though we have kind of orthogonality when we have different T1 and T2, there should be a function Q that is also a function of T1 and T2. And as you learned in signal-gen systems, for example, suppose you have x of t times delta of t minus t0, then if x of t is smooth enough, what? You have this equality, right? For example, you have x of t here, but you have at t0, you have an impulse. You multiply these two, and what? At every other place than t0, you have 0 anyway. So you have some impulse now with a height x of t0. So you have this equality. Similarly, suppose you have some q of t1 and t2 multiplied by delta of t1 minus t2. Then when the argument of delta function is 0, which means t1 equals t2, this survives. Otherwise, this q of t1 and t2 vanishes, anyway, becomes 0. So you may say that this equals q of t1 and t1, delta of t1 minus t2. Then, as we do usually in such a case, we may say that, okay, there exists a single variable function q that is now a function of t1, and you multiply delta. Of course, you may say that the argument is t2, but that makes no difference in this case. So this definition from our main text, Populis, is now understood in almost 30 years. Anyway, here goes another definition. A continuous time random process is called Y-sense stationary. If there is a constant C that is equal to the mean path for all t, and there is a single variable function that is equal to the autocorrelation function evaluated at t1 minus t2. It's a kind of review. Here goes an example, which is very important. You have a constant a cosine 2 pi f0 t plus uniform random variable theta on 0 to 2 pi, and f0 is not 0 hertz. And then, as we know, this is a Y-sense stationary random process and also 0 mean. And it has a very strange property, rememberable. It has a periodic component. It has a periodic component, but it's ergodic. Okay, so it's an example of Y-sense stationary and ergodic, but having a periodic component. Got it? And of course, this is ergodic in what sense? In the mean sense. Okay, so mean ergodic in the mean square sense, you may say that. So this is a very important example. And here goes, you may say that it's a theorem because it's very important, but we are not going to prove this. We are going to prove this later in the chapter 7 of the Peebles. Anyway, so the detailed discussion is deferred. But the theorem says that the autocorrelation function of at least Weiss and stationary real-valued random process cannot be an arbitrary function. It has some restriction. And the reason is not explained here, but there are some other small properties described here. The first one, we may say it's a lemma. In all these lemmas, we assume x is real valued and at least y and stationary. So we have additional assumptions for each lemma, or it's a simple consequence. The first one is that the real y and stationary random process has autocorrelation function that is symmetrical. And this is due to simply the commutativity of real multiplication. And second, the autocorrelation function is always bounded by its value evaluated at tau equals 0. So as we've seen in the previous example, even though it is stationary and ergodic and periodic, this R sub xx0 bounds the entire autocorrelation function. Got it? And this holds for general, at least y and stationary real valued random process. It seems I still have typos. Anyway, I would prefer that one. Anyway. And third one is that x is real, y and stationary, and has a periodic component. Then autocorrelation function also has a periodic, also has some component that has the same period. And this example is exactly matches to this lemma. The fourth one is that the real valued random process is y and stationary and ergodic with 0 mean and no periodic component. So this example is now excluded. And then the autocorrelation function tends to 0, which means that it decorrelates if the delay, the time difference is big enough. Lemma 5, stationary and ergodic and non-zero mean, but no periodic component. So this is again excluded. And in this case, we may define n of t by subtracting that constant, non-zero constant mean from x. Then obviously, n of t has 0 mean. And we have additional assumption. Autocorrelation function tends to 0, asymptotically decorrelates. Then what? The original autocorrelation function, when tau tends to infinity, converges to the square of the mean. And here goes an example. Suppose we have a stationary ergodic process having no periodic component and autocorrelation function given by this one. Then we can say that, okay, this is mean squared. The problem is that we don't know the sign. So we have plus minus 5. And we can compute the variance because this is the mean part and this is the power. So 4 is the variance. And last time we've stopped here without viewing the next figure. I just drew it. Suppose you have x of t, that is real y and stationary, and you multiply some carrier, or carrier is modulated by x of t. The important thing is that we have random phase here. If we don't have random phase, we have different result. Anyway, so it's a modulator. Now, the question is, what's the autocorrelation function and what is the property, second order property of the output of the modulator when x is y and stationary with this autocorrelation function? And as you know, the autocorrelation function of x looks like that. And now you modulate. And you simply use the definition of autocorrelation function of y. By the way, if x of t is stationary and that is stationary and ergodic, then what does that mean? Mean is 0, right? Because as tau tends to infinity or negative infinity, the autocorrelation converges to 0. So you know that, okay, y is stationary with mean 0, right? So first, let's compute the mean of y. What is that? Expectation of x cosine 2 pi f0 t plus theta. And if we assume independence of x and theta, then it's expectation of x of t and expectation of cosine 2 pi f0 t plus theta. And this is 0, and this is also 0, because we assume theta is uniform on this interval. Got it? Second, let's compute the autocorrelation function, plug in the definition, and with some manipulation, we can show that we have the input autocorrelation times cosine 2 pi f0 tau. And that is, again, a function only of tau. So in this case, the output is y and stationary too. Be careful. If theta is not a random variable, what do we have? So let's see. Suppose you have some z of t, that is x of t, cosine 2 pi f0 t plus theta, where theta is constant. Still, you may show the mean is 0 because x is a zero mean process. What about the autocorrelation function? And you have x of t plus tau cosine 2 pi f0 t plus tau plus theta. And you have x of t cosine 2 pi f0 t plus theta. Now you have r xx tau, and here you have cosine 2 pi f0 t plus tau plus theta times cosine 2 pi f0 t plus theta. And here there is nothing random, and if you use the trigonometric, one of the trigonometric identity, still you have the dependence on t. That means if theta is not random like this, then you don't have y and stationarity, so be careful. And also, in this original case, the output autocorrelation looks like the input autocorrelation modulated by cosine 2 pi f0 tau. So it's a very beautiful form. And we can verify the lemmas 1, 2, 3. The y of t is y and stationary zero mean, and it has symmetrical autocorrelation function. Its autocorrelation function is bounded by its its value at tau equals 0, right? Yeah, something like that. And also it decorrelates. So that's the review. And here goes the other things. So cross correlation. The definition is simple. Suppose you have complex valued x and y. You put t plus tau for the left side argument and t, and you put conjugation here. Okay. To real processes are uncorrelated if autocorrelation function can be written as a product of two, but for all pair T1 and T2, for all, okay? Not just one, for all pairs. They are, if statistically independent, then uncorrelated, as you've seen already. I mentioned that already, actually. Two real continuous time processes are orthogonal if the cross correlation function is 0 for all pairs of T1 and T2. Got it? Definition: two wise and stationary continuous time random processes are jointly wise and stationary. Actually, we've seen this already. If the cross correlation function is a function only of tau. Okay. So we have very simple consequence. If x and y are statistically independent and wise and stationary, then the autocorrelation function is just what? The product of two mean values. And if you have any difficulty, just rewrite this one. Okay. So you start from Rxy t plus tau t, and expectation of x of t plus tau, y of t conjugate if it is complex. And independence means that the expectation of product becomes the product of expectations. So you have this equality due to independence, and you have x bar and you have y bar actually conjugate. But here we assume the real, so I drop conjugation. And here goes some properties of cross correlation functions. And you see there are much similarities. This is a generalization of the properties of autocorrelation function because you can always take y equals x. Okay? If you take y equals x, then these should be the properties of autocorrelation functions. And let's see, in the first line, what does it say? The cross correlation function is is what? Be careful here. If you plug in negative tau, then you flip the order between x and y. Now, let's plug in x equal y, then what does that mean? R sub x of negative tau equals R sub x tau. That means, yeah, even symmetry, right? Even symmetry of the autocorrelation function. Second one, the cross correlation function is given, and you take the absolute value. And that is upper bounded by the square root of, what is this? Power of x and power of y. And you may say that this does not look like what I've seen already, but let's take this trick again. Then what does that mean? R sub xx of tau, absolute value, is less than square root of Rxx0. And this also becomes Rxx0. And the right-hand side is simply what? Rxx of 0. Got it? Because this is always non-negative. So if you remove the square root, then what? The autocorrelation function is always bounded by its value evaluated as 0. Okay. Third one is very simple. Actually, third one is a simple application of geometric, arithmetic and geometric mean inequality, right? As you've seen from your high school or middle school. Okay, this is too simple. By the way, how can we prove the first one? It's not that difficult because we again use the commutativity of the multiplication. Suppose we have the definition. And as we see here, we assume this is a function only of tau, right? So given that, let's start from the left-hand side. So you start with R sub xy of negative t, then what? You have expectation of x t minus tau yt. Am I right? Because instead of tau, you plug in negative tau. And then you flip the order. Then by definition, this becomes R sub yx, and you always subtract the right argument from left, so you have tau. Got it? So you have the result. It's just simple. Second one is a little bit tricky, but it's the proof is very important. You will see some similar proof when the process is complex value. And you may use this inequality to show the Pearson correlation coefficient, or simply correlation coefficient of two random variables is bounded by 1, something like that. So this is very useful, but proof is a high school math. So we start from this one, assuming x and y are real valued. So you multiply alpha to t. Let me see. I'd better flip this one. Okay. Yeah, still need many corrections. I'd better not use this one. Alpha xt plus tau plus y of t. Got it? So let's start from this. Since we assume x and y are real, and also let's assume alpha is some real constant. So real, and you square it. What happens? It's always non-negative, right? But these are random quantity. What does that mean? Yeah, it's with probability 1 is non-negative. You take the expectation. What do you have? Non-negative. For all real alpha. For all real alpha, right? Now, let's expand the left-hand side. And what do you have? You have 2 terms, right? 2 factors and 4 terms. And first one is alpha square and r sub xx 0. Why? Because you multiply x of t plus tau with x of t plus tau. The time difference is 0. They have the same time instant, right? Now you have cross term, alpha rxy tau, and you have what? Sorry, 2 times. And you have r y 0. Am I right? And this is always greater than or equal to 0 for alpha. What is that? It's simply a quadratic inequality. And by using the discriminant, then what? What you always do is this. Is it d over 2 or d over 4? I already forgot. But anyway, discriminant equals this square. Sorry. Minus 4, this and that. And what? Since you don't have any real root, no double root actually, it should be what? Something like this, right? Then you have this inequality. Got it? So now, this is a very interesting example. Suppose you have 2 real random processes, x and y. To generate the random processes, actually, you generate 2 random variables, a and b, in this case. A and b are uncorrelated zero-mean random variables with the same variance sigma square. Let's assume that. Got it? And we want to see for example, the cross correlation, autocorrelation, and those things. First question, x of t is y and stationary? Let me revise. What is the mean value, mean path of x of t? What is the mean path? And here, a and b are zero-mean random variables. So if you take the expectation of x or expectation of y, due to the zero-meanness of a and b, they are zero-mean processes. So x bar equals 0, y bar equals 0. Got it? Second, what about the autocorrelation function of x? Is it the function only of tau? What do you guess? So what you can do is that just plug into the definition. So you take t plus tau, t plus tau. Plus b sine 2 pi f0 t plus tau. And then you multiply itself. And then you have 4 terms, but your expectation makes the cross term disappears. So you have expectation of a square this times that, but we assume that they have the same variance. So you have cosine 2 pi f0 t plus tau cosine 2 pi f0 t plus sine 2 pi f0 t plus tau and sine 2 pi f0 t. And from one of the trigonometric identities, you know that cosine minus cosine, what is this? Is it cosine minus cosine? Cosine 2 pi f0 t plus tau minus 2 pi f0 t. Let me be careful. You have 2, right? Yeah. So is it correct? No, not 2. Sorry. Yeah. So you have sigma square cosine 2 pi f0 tau. Got it? I believe that is okay. Correct. And let's plot it. So your autocorrelation function of x is what? Yeah, it's a symmetrical function bounded by r sub xx0, which is sigma square, but has periodic component. Similarly, you can show that y has the same autocorrelation function. If I remember correctly. Now, the last question is what's the cross correlation function? And after some manipulation like that, you can show, if I remember correctly, you can show that cross correlation function is a function only of tau. But it's what? It's a odd symmetrical function. Got it? Yeah. Just a second. I believe I missed something. Okay, anyway. So is it correct? Yeah, I believe so. So cross correlation function is an odd symmetrical function. But anyway, it's a function only of time difference. So they are jointly wise and stationary. There is another approach to this one as a communication engineer. Is here is another approach. You use that real of something technique again. So the x of t can be written as real part of a minus jb e to the j 2 pi f0 t. And y of t can be written as real part of b plus ja e to the j 2 pi f0 t. So you can convert as a communication engineer. Whenever you see cosine and sine and cosine and sine, you can use this trick. And then it's a little bit sometimes easier to understand what's going on, or sometimes it's not. However, let's take a look at this complex valued kind of amplitude to the complex exponential. What about the mean and the variance and the complementary variance of this random variable? So expectation of a minus jb equals expectation of b plus ja equals 0, right? So the coefficient has 0 mean, right? So when you take the expectation of x, expectation operator passes through real part operator. And here, what is random? This is only random. So the 0 mean, this is kind of obvious. Second, what about the variance? Since we assumed A and B has 0 mean, and A and B are uncorrelated, having same variance sigma square, what is the norm scale of this one? As we know that the modulus scale, modulus of a complex number is the scale of real part. Modulus scale of complex number is the scale of real part and scale of imaginary part. So you have what? This is expectation of A square plus expectation of B square, always. So it's 2 sigma square. And what about the complementary autocorrelation? Complementary variance. So you have ordinary square, and you have now 4 terms. But you can rearrange like this. And what? They are 0 mean uncorrelated, so this cross term disappears, and you have same variance, so it's 0. So interestingly, you are expecting that these 2 random processes are proper complex because they are proper random variables. Got it? Proper complex constant random process. So given this real bandpass random process and this real bandpass random process, their complex baseband equivalents are complex random variables that are proper. Okay. And there are some theorems, like suppose you have a real valued bandpass random process, and if their complex baseband equivalents are 0 mean, jointly wise, and stationary, then their real valued bandpass counterparts are also wise and stationary, blah, blah, blah. So you will see that later if we have enough time. Okay, let's move to the other definition, which we already have done. But this is autocovariance function. So you subtract the means. Cross covariance function. So you again subtract the means. For at least the joint wise and stationarity, you have these properties which are very simple. Variance, we have already defined. Uncorrelated, you can use the autocorrelation function or autocovariance function to define the uncorrelatedness and other things. Okay, for the discrete time, I haven't yet completely corrected here. I want to move there, so I will update and upload the note. Okay, the last topic in Peebles chapter 6 is the measurement of correlation function. This is a very short section. However, it's very, very important. And also it relates our knowledge on ergodicity and also correlation function. As the first line says that in the real world, we can never know the true correlation function of 2 random processes. But we still want to make statistical inference. So what do? We make a lot of assumptions and quantify something. Okay, that's the problem of human life. So the situation is like this. Suppose X is a Kospi index, and Y is New York Stock Exchange index, like Dow Jones or something. Got it? And you want to find some dependency However, dependency, that term sounds too strong. So what you want to extract is kind of second order information. Means you want to estimate or you want to have a rough idea of the cross correlation function between these two. And of course, as I mentioned the last time, the stock market indices are not zero mean processes. They may have seasonal periodicity. They may have weekly periodicity. For example, many day traders want to sell everything by Friday because they never tolerate the weekends where they cannot sell or buy any stock. For example, you may have some terrorist attack during the Sunday, and you know that on Monday 9 a.m. your stock will plunge. They cannot tolerate, so they sell everything by Friday. Day traders, okay. So due to the existence of that kind of humans in the market, you have weekly periodicity. As I told you, you have monthly periodicity, seasonal periodicity, something like that. So this is too much simplified. What you usually do is that you have Kospi, you have Dow Jones, and you pre-process, okay, and make them equivalent zero mean wise and stationary processes. Or you believe, okay, now after I subtracting something and scaling something, it seems, and I believe it's wise and stationary enough. And here goes your another bold assumption. They are jointly wise and stationary. And actually jointly ergodic. And then you do this. Okay. So here goes one single sample path of X. And here goes one sample path of Y. And what you do is that simply delay by capital T and delay by capital T minus tau, or you may just take T equals 0. So yeah, anyway. I really hate this. Just a second. Just a second. Yeah. Delay by capital T plus tau. The reason why we do is that here we set time t equals 0. Okay. So I am here. So I observe x of t for t less than 0. And I also observed y of t for t less than 0. But I want to do some time average from t1 to t1 plus to capital T. So what I'm going to do is that actually I take some chunk of the past observation with period 2t. It shouldn't be necessarily 0 to negative 2t. It could be any period 2t that encloses x of t and y of t without discontinuity. So don't be too much paying attention to the integration interval. What is important is just you take some long enough period of past observation. And what you do is that you have different delays. And you use that delay as the delay in your autocorrelation function. So what you want to estimate is this one. You want to estimate that one. So what you do is that, okay, I have x of t, I have x of t plus tau, y of t, or I have x of t, y of t minus tau, and dt. and integrate over some 2t period. And I will divide the quantity by the period. And as we've seen already, if capital T is large enough, this is very close to the time average of what? Time average of x of t plus tau y of t. What is our ergodic assumption? We may assume x and y are cross correlation ergodic. What does that mean? We replace the time average. Sorry. You may say, okay, this is x, okay? You may replace the time average with the statistical average. That is the assumption. So here, if x and y are cross correlation ergodic, then this is justified. What does that mean? If you have finite interval, then this time average is close enough to your ensemble average. So this is the way, okay? And here plus, minus, or interval doesn't matter. What is important is that you take a continuous chunk and you make a delay for large, you make large enough delay, okay? So you will never use what is not observed for tau. Okay? So this is the way to estimate the cross-correlation function. This is the simplest one. And you will see more sophisticated refinement here, because here we just take a chunk of observation. Sometimes we multiply a window to remove some discontinuity or other things. And that is the topic of so-called spectral estimation. And you may say that, where is spectrum? Where is frequency? But in every time domain estimation has its frequency domain counterpart. So you will see some kind of periodogram, spectrogram, blah, blah, blah in spectral estimation theory or course, which unfortunately I'm not going to cover. But now you know the core in this measurement of correlation function. What you do is that you make a lot of assumptions, and from realizations, single observations of x and y, you want to make you estimate the statistical correlation. So what you do is this one, and you approximate left-hand side by doing that one or that one. Got it? And what kind of things can you do by doing this one? As I told you, we can use this trick to build some machine learning model that will work on the stock market, or you can even do some noise cancellation. And this is kind of the idea of almost every statistical filtering theory. You assume, okay, my observations are stationary and ergodic in some sense. So that's why you see a lot of theorems starting with given a stationary and ergodic random process, blah, blah, blah. Given jointly stationary and ergodic random processes, blah, blah, blah. Otherwise, you can never use this trick. Time average equals the statistical average. So that is the most popular assumption. And also, that makes everything work, and that makes every real situation very dangerous, because you never know your ergodic assumption is correct or not. Okay. Okay, I will not talk too much about this one. Now let's move to, am I right? Just a second. Yeah, just a second. Which one is better? Yeah. Okay, got it. So unlike what I talk, still it seems I'm talking about this convergence, but anyway. So this is chapter 7 of our main text populist book. And the title, actually section 7.4, stochastic convergence and limit theory. The biggest difference between undergraduate level and graduate level probability and random process courses is this one. Usually in undergraduate course, we never talk too much about this one because students feel horrible whenever professor talks about the limit and convergence of a sequence, blah, blah, blah. And now it's a convergence of a sequence, not of real numbers, but of random variables. So it's much horrible, sounds horrible. But anyway, what I'm going to do is that I will review the convergence of a sequence of real numbers first. Anyway, I believe most of you have forgotten that part already. So, unlike your expectation, let me start with equality versus approximation. Approximate equality of two real numbers, okay? So it's not bad, okay? The two numbers. Suppose you have the irrational number pi, okay? What is that? What's the definition of pi? That is the ratio between the circumference of a circle to the diameter, right? So the circumference is approximately 3 times the diameter, or you may say, no, 3.14 blah, blah, times the length of diameter, right? By the way, the Bible in one of the Old Testament says that the circumference of a circle is 3 times the diameter. So according to the Bible, pi is 3. Okay. Anyway, so suppose we already have defined the subtraction and blah, blah, blah. And now this is not that mathematically correct. You may say that it's preposterous. 전후 관계가 뒤바뀐. But anyway, so suppose you have two real numbers, x and y. And given two real numbers, we either have two equal numbers or two different numbers. Obvious, right? I didn't say two identical numbers, so they are either equal or different. And here goes not a lemma, exactly speaking, but let's say it's a lemma because it's very important. X equals y if and only if x minus y equals 0. And you may say that it's same statement, but it's very important, okay? Whenever you want to show two real numbers are equal, you can just subtract them and compare the result with 0, okay? That is very important in engineering sense, okay? So x equals y if and only if, that means equivalent to x minus y equals 0. And also there is another one. If and only if x minus y is less than or equal to 0 and x minus y is greater than or equal to 0. You may say that is too redundant. And also same is absolute value of x minus y is less than or equal to 0. This is too, how to say that? Just tricky, right? It's obvious, right? Because absolute value of a real number is always greater than or equal to 0. And it says less than or equal to 0, means it's 0. And if absolute value of a real number is 0, if and only if that real number is 0. So x equals y. So far it's too obvious and you don't understand why I talk that, but in many engineering sense, here goes the important thing. we just have finite resolution. Okay, we have some measurement error. So we never have two exactly identical numbers. Current, voltage, no identical, right? Not exact, but within some error or margin, right? So it's more important to talk about approximate equality than exact equality. Of course, in your math exam or qualifying exam, equality is very important. And some question says that, what is this value? You may say that it's a real number. That is correct, but your professor didn't want that answer, right? Exact x equals pi minus blah, blah, blah. Now, let's compare the previous two obvious statements with this one. Now, two real numbers, x and y. Okay. Let's, okay. Before doing this, let's do this first. X equals y if and only if the difference has what? Is less than or equal to epsilon for epsilon positive. And you may say that, why this isn't? Why? For all epsilon positive, the difference is less than epsilon. Here, the important thing is that epsilon cannot be 0, but can be taken arbitrarily small. So you take, for example, epsilon equal 10 to the negative 11. And what does that mean? X minus y is less than or equal to 10 to the negative 11. You take 10 to the negative million, trillion. X minus y is less than or equal to that epsilon. Is this statement for every epsilon positive, absolute value of the difference is less than that epsilon? Does that mean x equals y? If so, why? Of course, this can be proven with using the proof by contradiction. Okay. So what you do is that suppose x minus y is not equal to 0. Okay. Then you have this number, some finite number, positive, right? And then you can easily find epsilon that is smaller than that. So even though this looks strange, this is the same as x equals y. Ready? Also, you may say that, so it's a kind of warming up, okay? If and only if can you say this? Right? Again, using the proof by contradiction, you can show that x equals y if and only if this holds. Right? Yeah. You can do proof by contraposition, proof by contradiction anyway. So this is this one, but hey, spend 1 minute to see whether or not this is wrong or correct, but do not use that. Now, so you warmed up. Let's talk about approximate equality. As I told you, you want to say x is approximately equal to y, or x minus y is approximately equal to 0. So how can we handle that statement mathematically? In many engineering problems, we need this. In real life, we need that. The first thing is bounding, as I once told you. And second one is that, strangely, you construct a sequence of real numbers. Strange, right? Sequence of real numbers, and talk about convergence. Okay. So here goes some strange thing. Suppose you have a sequence of real numbers, x sub n, and a real number y. Okay, and here for all n, xn is never equal to y. For example, something like this. Here, we have an example. Xn equals e to the negative n. Then what do we have? And you know e to the negative n tends to 0 as n tends to infinity, right? So suppose here y equals 0 and xn equals e to the negative n. Then each xn is never equal to y. But we know that for sufficiently large n, xn is very close to 0, right? And the convergence of a sequence makes this kind of statement precise. And here goes the definition. And you really hate. For every epsilon positive, okay? So we do not use equality here, okay? So it's our spell, our memory starts for every epsilon positive. I never said for every epsilon non-negative, okay? I say for every epsilon positive, there exists some number, n, of epsilon. That depends on our choice of epsilon. And actually, this is a natural number, okay? And such that, and as we've seen here, this inequality can have equality or not. It doesn't matter, okay? As I've already told you here in the, in this case, okay? Yeah, here and there, as far as epsilon is positive. And for sufficiently large n, the difference is less than or equal to epsilon. So here, whatever epsilon you take, I can find some n of epsilon. And if n is greater than or equal to n of epsilon, the difference between 0 and e to the negative n is less than epsilon. If we can find n of epsilon for every epsilon positive, then in that case, we claim this sequence converges to the limit y, okay? But in an engineering sense, what is important? We want to say that xn is approximately equal to y for sufficiently large n. Okay? So approximate equality, to talk about approximate equality, we construct a sequence of real numbers and show that converges to the limit, the target. Got it? So whenever you confront some situation like this, okay, even though there is no sequence at all, construct a sequence. Got it? And so far, you may say that it's simple, but here goes the difficulties. First, by the way, here, x, or in this case, y, is the target of the limit operation is called the limit. Okay. And this definition, as you notice, has what? Has the target already. You have a sequence and you have a target. And as I once told you, Cauchy wanted to remove the knowledge on the target. And can we find some property by just examining the sequence only? And Cauchy have found that. And especially for the sequence of real numbers, he found that some property is met only for the sequences. The limit exists, which means that the sequence converges to a finite real number. And I'm not going to talk about that right now, because anyway, we will see that soon. And here goes some notations. limit of xn equals 0 as n tends to infinity, or n goes to infinity. Okay, so they read almost the same. Okay? But we usually say limit n infinity xn equal x, and that's okay for non-native. But sometimes we just read this one as if we have definition for every epsilon positive. And this does not sound like our definition, but the difference between xn and x is less than or equal to epsilon for sufficiently large n. Okay, so it does not say n tends to infinity. It says for sufficiently large n. Also here, xn is approximately equal to x for sufficiently large n. So you always remember, okay, in many engineering problems, you make approximation. But you want to show that, prove that mathematically, more rigorously, then construct a sequence and prove the convergence. Of course, not only showing the convergence is important, but also showing the rate of convergence is also very important. As you know, 1 over x converges to 0 very, very slowly, right? 1 over x squared converges much faster. E to the negative x converges much, much faster, so to 0. So rate of convergence is also very important. But in many engineering problems, proving or deriving the rate of convergence is very difficult. So what we usually do is that after we prove it converges, we usually run a lot of simulations and showing that the convergence is fast enough. Okay. Now, yeah, here goes the definition. I put the definition of Cauchy sequence here. A sequence xn is called a Cauchy sequence if you should be careful here. I didn't provide any limit. For every epsilon positive, that is still the same. There exists n over epsilon, a natural number, that is still the same. And here, such that you have two indices, m and n. Before, in the definition of the limit of a convergence of a sequence to a limit, involved only one parameter, but here two parameters, m and n. Both of them are greater than or equal to your choice of n over epsilon, or your finding of n over epsilon. And implies the difference between two values is less than or equal to epsilon. And be careful. Before, one of them was x, the limit. But here, no limit. Okay? And if a sequence just satisfies this property, then you say that the sequence is a Cauchy sequence. And Cauchy has found a very interesting thing. If the sequence is real numbered, then Cauchy means convergence. And convergence means the sequence is Cauchy. Very interesting. So without the limit, he showed he kind of defined the convergence of a sequence again. However, many different attempts of expanding or extending this idea of Cauchy sequence failed actually. For example, you have a sequence of some strange thing, and it exactly satisfies the definition of Cauchy. So it's a Cauchy sequence in some space. However, it never converges. Something like that. Got it? So what kind of example do we have? Just a second. Maybe this will work. So here I say it's real, right? So consider sequence of complex numbers on a unit circle. And suppose z sub n equals, no, I do not want to do this. Just a second. Yeah, okay. It may work or not. I'm not sure. Okay. Yeah, something like this. Am I correct? Yes, it's not true. Okay. No, this sounds very dangerous. I won't do this. Okay. Yeah. I will provide the kind of example in a complex domain later. Now let's expand our kind of exercise to real valued functions. Okay. Because as an engineer, we not only say this value is very close to that value. Sometimes we plot or draw some graph of a function and say that two graphs are very similar, which means that the two functions are approximately equal, right? Suppose as a mechanical engineer, you design a very small part in your machine that is nanoscale or some angstrom scale. And you want to say that the surface of this product is almost the same as the original design with margin some less than something. So comparing two functions is also very important. And in engineering problem, you want to claim that these two functions are almost the same. Same thing. So what you do is that, suppose you have function x and y, and you may say that it looks like a random variable. Actually, what we are going to do that is that direction. We are going to view random variables as a function, as we defined in the measure theoretic sense. So this kind of approximate equality of two functions is closely related to the approximate equality of two random variables. And almost the same thing occurs. But since we are timed out today, let me continue this Thursday. Okay, that's all for the day. And I forgot that I postponed the due of homework 11 to this Thursday, even though many of you already turned in.